Hi, welcome to the lecture number 12. In this lecture, if you remember the last lecture, the lecture number 11, there we discussed about mostly the OCV concept, how the OCV modeled into the STA, and what are the sources of the OCV, and how we can model into mathematical expression. So in this lecture, we tried to see with that, we tried to calculate the maximum and minimum timing analysis. This is setup and hold. You know that with OCV constant. So we tried to calculate. We will calculate the three things. One is without OCV, with OCV, and with OCV plus CPP. That common path pessimism removal. So let's start with that OCV example we taken. I think several times you saw this diagram. I don't need to discuss about again and again. So if you see carefully that I mentioned one launch path buffer insertion and capture path buffer insertion with timing, and I mentioned the whole timing total as from this clock to Q point to D2 point, that capture fluff is a 6 nanosecond, and my T clock here is a 7.2 nanosecond, and T setup time is a 0.5 nanosecond. So when you go to solve, there this type of things will mention that setup time in derate early is 0.85 nanosecond, 1 nanosecond for the derate late, and this cell check derate. Okay, let's start with the calculation actually. So first we will calculate that launch clock plus data path, which is this is the launch clock path and this is the data path. So total launch clock path plus maximum data path, this is the total. So 1.5 nanosecond plus 0.9 nanosecond plus 6 nanosecond into how much? This is the late. We have to multiply with that late derate. So this is 1.1 nanosecond. So how much it will come? It will come as a 9.24 nanosecond. Now calculate the capture clock path, where this one is 1.5 nanosecond and 1.1. So 1.5 plus 1.1 multiplied with this 0.85. So this will come as a 2.21 nanosecond. We have to multiply actual setup time here. T setup is already mentioned 0.5, but here it is also mentioned that setup timing late derate 1.05 nanosecond, which is actually we have to multiply. So this is 0.5 multiplied 0.5 multiplied with 1.05, which is come as a 0.525 nanosecond. Now it is very simple that we have to calculate the slack, and this is the slack in OCV case. I have to calculate the difference between the data required time minus data arrival time. Those things I think you know very well. I discussed several times. So which is like data required time is how much? That 7.2 nanosecond is the T clock period with 2.21 minus 9.24 plus 0.525, which came as a 0 minus 0.525. 0.355 nanosecond. So obviously there is a what? There is a slack is negative. So it means that there is a setup violation. But apparently it shows as a setup violation because we didn't consider the CPPR case, OCV plus CPPR, because we use this common clock path in both like launch clock and capture clock. So we calculate that same clock path at the same instant of time into the two, like we multiplied with late direct also and early direct also. So we have to calculate the CPPR. That CPPR should be like 1.5 into late direct minus 1.5 into 0.85, which is the early direct. So it will come as a 375. So now actually slack will be OCV plus CPPR is minus 0.355 plus 0.375, which will come as a 20 picosecond. So it's a positive number. So now we can say that this is a positive slack, or you can say no setup violation. So I think you understand that why CPPR calculation is most important here, because it will add a buffer time to a slack which can mitigate the slack as a positive and setup violation, no setup violation. So this is the case we consider about the max delay on mostly the setup calculation. Now coming into the part for the hold. How to do that? Let calculate first case, which is with OCV. What will be that case? So here that launch path, minimum data path, which path it is? This is the launch path and this is the minimum data path. I think you understand. So this is something is how much? 0.4 plus 0.6 plus 1.5 multiplied with setup timing direct early 0.85 nanosecond. It is already given. So how much it is coming? 2.125. Now calculate the capture clock path, which is 0.4 plus 0.9 multiplied with 1.1, 1.43 nanosecond. The whole time, which is how much it is given? 0.9. So the T hold actually after direct 0.9 into 0.9, 0.81 nanosecond. So slack here is data arrival time minus data required time, and data arrival time is how much here? 2.125 minus 1.43 minus 0.81, which is came as a minus 0.115 nanosecond. So obviously because of that negative slack, so there is a hold violation, but again we have to calculate with OCB plus CPPR case, where we just have to calculate that CPPR, which is how much? We have to multiply the 0.4 1 with 1.1 and 0.4 with 0.85. So 0.4 into 1.1 minus 0.4 into 0.85. How much it is coming? So now the slack OCB plus CPPR is minus 0.115 plus 0.1, which is still as a minus 0. But very less number. So still there is a violation, hold violation. Okay, so it can be do better with buffer insertion. I think it can easily, we can do that. So with these two example, how that setup time and maximum time and minimum time we can calculate in the constraint of OCV, and also not OCV with common path pessimism removal. So I think and I hope that you understand with that example. Thank you for listening this video with your patience. Thank you.